Hi, students. Welcome to video 9. It is on population ecology. So after this video, you should be able to describe ways that we can characterize and classify populations. You also should be able to do calculations to calculate the change in a population over time. You need to be able to describe carrying capacity and the impact that has on ecosystems and explain how resource availability affects population growth. So when we talk about populations, we're going to have 5 different characteristics that we're going to go through. And for each one, we're going to give examples of how we actually measure these different things. So the first one is population size. You'll see it as either little n or big N if you're talking about total populations. So in this situation, our big N is 9 rabbits. However, we can have rabbits die, and then we would have a N of 7, or we could have rabbits be born, and then we would have an N of 10. We can also talk about the density of the rabbits. So this will be a low density situation. They're all spread out versus a high density situation. They're all kind of clumped together. So the distribution of the rabbits can also be 3 different types. So we can have random distribution. They're just kind of all over the place, no rhyme or reason. We can have uniform distribution. They're kind of equal distance apart. This is very unusual in nature, and you usually will not see this with animals. It'll be more of the plants that are be uniform. Or the most common one with animals is going to be a clump distribution. Think about lions with their prides, wolves with their packs, zebra herds, things like that. The reason clumped is the most popular is because this provides protection from predators and other animals that would want to try to hurt the group. It's harder to get at the individuals if they're in clumped groups. So we can also look at sex ratios. We can say how many are male, how many are female. So we have pink versus blue. And we can also do an age structure diagram for these different animals. So you'll see that the larger rabbits represent the older rabbits, and then the young ones are the small ones. So if you put them in an age structure, you kind of make like a pyramid shape. And the young rabbits go on the bottom, the older ones go on the top, and then you also have them separated male and female. So let's talk about how to do a population change formula. So anytime you see N sub O when dealing with population, that is our initial population amount. So make sure you're can identify that later on. So in this initial population of rabbits, I have 10 rabbits. We're going to calculate a change in the population of rabbits. So how many births minus deaths plus immigration minus immigration. Okay, and if you need to know what those words mean, here's your births and immigration are people coming into the population or rabbits coming in. Deaths and immigration is people leaving the population. Okay, so for this population of rabbits, let's have 3 rabbits are born. So my B in this case will be 3. We're going to have 1 rabbit die off, so it went away. We're going to have 1 rabbit immigrate, come into our population, and we're going to have 2 rabbits emigrate, go away from our population. So once you add those numbers and subtract, you end up getting a change of only 1 in this population. So now we've calculated a change, we can also calculate a growth rate. So how much did I grow? Or we can have a decrease. How much did I decrease by? So our formula for growth rate is always going to be change in N divided by the initial population. So how many did I add or subtract divided by what did I actually start with? So in this situation, we calculated our change in N was 1, and then we said that our initial population was 10. Okay, so 1 divided by 10 would be 0.1, and then if you want it to be a rate, you multiply by 100, and so you would have a change of 10% in this population. So no population can increase indefinitely. There's always going to be some sort of environmental factors, environmental resistance to an increased population. So we call it increased growth rate or biotic or intrinsic growth rate is the same thing as biotic potential. And these are the rate of population would grow if it had unlimited space, unlimited food, water, nothing was impacting the population. So there were no limiting factors on our population. And we know that in reality, that is not ever the case. It might be the case for a little while, but eventually you're going to have factors limiting the resources. So our carrying capacity is going to be that max population that we can sustain. And oftentimes you'll see it labeled as K. So here are some pictures of those words. So here's our biotic potential. We're growing and growing and growing. There are no limiting factors acting on us. Once we hit this environmental resistance, these are my limiting factors. So now I ran out of space, I ran out of water, I ran out of food. That's also our carrying capacity there. So this first part of the graph is an exponential growth curve. That would be a J-shaped growth. So you need to know that both J-shape and exponential growth are interchangeable. And then once I hit this flat line, now my shape has moved from J to an S. So see this S symbol right here, S shape. And the S curve is also called logistic growth, and that's when I have hit a carrying capacity and my environmental factors are impacting my population. So what happens if I don't actually level off after I've hit my carrying capacity? We can have a population overshoot. So here is our carrying capacity is this orange line down here, but something has happened to where our caribou or our deer population can continue skyrocketing. Maybe there was a lot of food at one point, but then we had too many individuals because of all that food, and then you end up having a population crash. So this population crash is called an overshoot, where I overshot my carrying capacity, and then now I'm going to have a die-off of individuals because I am actually having environmental factors resisting my exponential growth, but it hasn't caught up yet to what I'm actually seeing. Okay, so now I've hit carrying capacity, and I usually hover somewhere around there. It's not going to be an exact flat line. This is a more realistic graph. So I can have a bunch of different population curves. The one up here that you see with the lynx and the hare, this will be a predator-prey graph, and that is a cyclic population curve. So please make note of that. Predator-prey is a cyclic curve. You can also have a stable curve, which is pretty much I'm at my carrying capacity. And I just hover up and above, below that a little bit, and I'm pretty much stable. Irregular, we really don't understand irregular population lines, graphs. We don't understand why this is happening. Maybe eventually we will, but they just kind of look random and we have no clue what's going on. Then we have eruptive. This is like that overshoot that we saw. So you are pretty stable for a long time, and then all of a sudden you erupt. You have a lot of individuals. For some reason, maybe you have a lot of food that year, but then eventually you're going to fall back down to your carrying capacity. So one case study that we talk about a lot is, and you're probably familiar with the white-tailed deer in North Carolina. It's not just North Carolina, it's a lot of the United States. This species of deer almost went extinct before they were protected in 1920, so they almost completely died out. Now there's a ton of them, okay, millions of them in the United States. And unfortunately, they pose lots of problems. One of the biggest ones being vehicle collisions. So there's a ton of people that die every year because they actually hit deer. 1.5 million is the number for how many collisions actually happen, but not the deaths. They also transmit diseases like Lyme disease, deer ticks. The ticks can bite the deer, and then they carry Lyme disease to people. So this is one reason why we have opened up hunting season for deer, and we encourage people to go and actually hunt deer because they cause so many issues. Now, in a way, it's not really the deer's fault because they're just, mating and doing their thing. But humans are kind of encroaching on their population. So the more we urbanize, the more we grow out into their environment, the more collisions and issues we're going to have with these animals. All right, that's it. Bring your questions to class.